The National Electrical Code, or NEC, mandates that the equipment grounding conductor, known as the EGC, must be continuous throughout the entire electrical system. This continuity extends from the service entrance all the way to the equipment it serves. The primary purpose of this requirement is to ensure a low impedance path for fault current, facilitating the quick operation of overcurrent protective devices like circuit breakers or fuses, thereby minimizing the risk of electrical shock and fire. The NEC specifically prohibits the interruption or breakage of the EGC by any means. This includes devices such as ground lugs, split bolts, or any other similar connection methods that might compromise the integrity and continuity of the grounding path. The reasoning behind this prohibition is rooted in the potential for these devices to introduce points of failure in the EGC system. If a ground lug or split bolt were to fail, it could interrupt the EGC, creating a safety hazard by increasing the impedance of the grounding path. This increased impedance can delay the clearing of a fault, increasing the potential for equipment damage and electrical shock. In a typical electrical system, the EGC must be a single continuous wire or conductor that is not interrupted by any intermediate devices. This continuous conductor ensures a reliable and low impedance path for fault current to flow back to the source, enabling the rapid tripping of the overcurrent protection. There is an exception to the rule requiring a continuous EGC. This exception applies when the neutral bus is grounded to the panel can. In this specific scenario, the EGC can be connected to the neutral bus instead of directly to the panel can. However, it is crucial to understand that this exception is only permitted if the neutral bus itself is properly grounded in accordance with the NEC. Proper grounding of the neutral bus ensures that it is effectively connected to the earth, providing a low impedance path for fault current. This configuration maintains the integrity of the grounding system, even though the EGC is not directly connected to the panel can. When grounding the neutral bus to the panel can, it is essential to adhere to the specific requirements outlined in the NEC. These requirements typically involve using appropriately sized grounding conductors and ensuring that the connection between the neutral bus and the panel can is secure and reliable. The size of the grounding conductor is determined based on the size of the service entrance conductors, as specified in NEC Table 250.66. In practical applications, it is often recommended to ground the neutral bus to the panel can and then connect the EGC to the neutral bus. This approach helps to ensure that the EGC is effectively continuous throughout the entire electrical system, providing a reliable and safe grounding path. This configuration offers a redundant grounding path, enhancing the overall safety of the electrical system. In a multi-story commercial building with a 30 kV transformer fed from a 1200 amps bus supplying a 225 amps panel, the EGC must be continuous from the 1200 amps bus all the way to the 225 amps panel. This means that the EGC should be a single, unbroken conductor without any interruptions caused by ground lugs or split bolts. The NEC does not permit the use of these devices to connect the EGC to the panel can because they can potentially create points of failure in the grounding system. To ensure compliance with NEC and to maintain a safe and reliable electrical system, it is recommended to ground the neutral bus to the panel can and then connect the EGC to the neutral bus. This configuration ensures that the EGC is continuous throughout the electrical system, providing a low impedance path for fault current. It is important to consult the latest edition of the NEC and to consult with a qualified electrical inspector or engineer to ensure that the grounding system is properly designed and installed. Correct grounding is crucial for the safety of personnel and the protection of equipment. The NEC provides detailed guidelines and requirements for grounding electrical systems, and it is essential to follow these guidelines carefully to ensure a safe and compliant installation. Furthermore, it's vital to understand the difference between grounding and bonding. Grounding refers to connecting an electrical system to the earth, while bonding involves connecting different metallic parts of the electrical system together to create a common electrical potential. Both grounding and bonding are essential for electrical safety. The equipment grounding conductor plays a crucial role in both grounding and bonding. It provides a path for fault current to flow back to the source, allowing overcurrent protective devices to operate. Additionally, It bonds the metallic parts of the electrical system together, minimizing the potential for voltage differences that could create a shock hazard. To further elaborate on the importance of a continuous EGC, consider a scenario where a fault occurs in a piece of equipment. If the EGC is not continuous, the fault current may not have a low impedance path back to the source. This can result in a delayed tripping of the overcurrent protective device, allowing the fault current to flow for a longer period of time. This prolonged flow of fault current can cause overheating of conductors, potentially leading to a fire. Additionally, it can create a shock hazard if a person comes into contact with the faulty equipment. By ensuring that the EGC is continuous, the fault current is provided with a low impedance path, enabling the overcurrent protective device to quickly interrupt the circuit. This minimizes the risk of fire and electrical shock. In addition to the continuity requirement, the NEC also specifies the minimum size of the EGC based on the size of the overcurrent protective device protecting the circuit. The size of the EGC must be sufficient to safely carry the maximum fault current that could occur in the circuit. NEC Table 250.122 provides guidance on the appropriate size of the EGC based on the rating of the overcurrent protective device. It is important to consult this table to ensure that the EGC is adequately sized. When installing the EGC, it is crucial to avoid any sharp bends or kinks in the conductor. Sharp bends can increase the impedance of the grounding path, reducing its effectiveness. Additionally, it is important to ensure that all connections are tight and secure. Loose connections can also increase the impedance of the grounding path and create a potential point of failure. Proper installation and maintenance of the EGC are essential for maintaining a safe and reliable electrical system. Regular inspection should be conducted to ensure that the EGC is in good condition and that all connections are tight. Any damaged or deteriorated EGC should be replaced immediately. In summary, the equipment grounding conductor must be continuous throughout the entire electrical system, from the service entrance to the equipment it serves. The NEC prohibits the use of ground lugs, split bolts, or other similar devices to interrupt the EGC. The only exception to this rule is if the neutral bus is grounded to the panel can, in which case the EGC can be connected to the neutral bus. Proper grounding and bonding are essential for electrical safety, and it is important to consult the NEC and to consult with a qualified electrical inspector or engineer to ensure that the grounding system is properly designed and installed. It's also worth mentioning that different types of equipment grounding conductors exist, each suited for specific applications. Firstly, there's the Y-type EGC, typically a solid or stranded copper conductor, used extensively in branch circuits and equipment wiring. Secondly, metallic raceways, such as rigid metal conduit or electrical metallic tubing, can serve as EGC if properly installed with approved fittings. Thirdly, cable trays, under specific conditions outlined in the NEC, can also function as EGC, providing a continuous grounding path for cable installations. Fourthly, equipment frames can serve as EGC if they are reliably connected to the grounding system, ensuring that all metallic parts of the equipment are at the same electrical potential. Fifthly, the green insulated grounding wire found in flexible cords, used for portable appliances and equipment, provides the direct grounding path back to the power source. When selecting an EGC, consider factors such as the available fault current, the length of the circuit, and the environmental conditions. The EGC should be sized to safely carry the available fault current without overheating, and its length should be minimized to reduce impedance. Also, the EGC should be protected from physical damage and corrosion to maintain its integrity over time. Furthermore, it's crucial to understand the concept of impedance in grounding systems. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. A high impedance grounding path can limit the flow of fault current, delaying the operation of overcurrent protective devices and increasing the risk of electrical shock and fire. Therefore, it's essential to minimize impedance in the grounding system by using appropriately sized conductors, making tight connections, and avoiding sharp bends in the EGC. Regular testing of the grounding system is also recommended to verify its effectiveness. Ground impedance testers can be used to measure the impedance of the grounding path and identify any potential problems. Any issues identified during testing should be addressed promptly to ensure the continued safety and reliability of the electrical system. In addition to the NEC requirements, local electrical codes and regulations may also apply. It's important to consult with local authorities to ensure compliance with all applicable codes and regulations. Local codes may have more stringent requirements than the NEC, and it's essential to be aware of these differences. Proper grounding is not only essential for safety, but also for the proper operation of sensitive electronic equipment. A well-designed grounding system can minimize electrical noise and interference, improving the performance and reliability of electronic devices. Therefore, it's important to pay attention to grounding when installing and maintaining electrical systems that serve sensitive electronic equipment. In conclusion, understanding the NEC requirements for continuous equipment grounding conductors is crucial for ensuring electrical safety and code compliance. By following the guidelines outlined in the NEC and by consulting with qualified professionals, you can create a safe and reliable electrical system that protects people and equipment from the hazards of electricity. This also includes understanding the differences between grounding and bonding, selecting the appropriate type of EGC, minimizing impedance in the grounding system, and regularly testing the grounding system to verify its effectiveness. Remember that electrical safety is paramount, and proper grounding is a fundamental aspect of electrical safety. So take the time to learn about grounding and bonding, and always follow safe electrical practices. The information provided here is intended for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician or electrical engineer for any electrical work or questions. They can provide you with specific guidance based on your individual circumstances and ensure that your electrical system is safe and compliant with all applicable codes and regulations. The importance of maintaining a low impedance ground fault path cannot be overstated. The lower the impedance, the greater the fault current, and the faster the overcurrent device will operate, thus minimizing damage and shock potential. The NEC provides tables such as Table 250.122 to assist in selecting the proper size EGC based on the overcurrent protection device. In some instances, an equipment grounding conductor may need to be larger than what is shown in Table 250.122 to minimize voltage drop under fault conditions, especially in long circuit runs. Voltage drop can impede the performance of overcurrent devices, and in extreme cases, prevent them from operating at all. In addition, it's crucial to differentiate between equipment grounding conductors and grounded conductors, also known as neutral conductors. The equipment grounding conductor is a safety conductor intended to provide a path for fault current, while the neutral conductor is a current-carrying conductor used to carry unbalanced current back to the source. These two conductors should only be connected at the service entrance or at a separately derived system, such as a transformer. Connecting the neutral and ground conductors at any other point can create a parallel path for neutral current, which can cause nuisance tripping of overcurrent devices, create ground loops, and increase the risk of electrical shock. The NEC provides specific rules regarding the bonding of metal enclosures and raceways. All metal enclosures and raceways that contain electrical conductors must be bonded together to create a continuous electrical path. This bonding ensures that all metal parts of the electrical system are at the same electrical potential, minimizing the risk of electrical shock. Bonding can be accomplished by using bonding jumpers, bonding bushings, or other approved bonding methods. The NEC also addresses the use of surge protective devices, or SPDs. SPD are used to protect electrical equipment from voltage surges caused by lightning strikes, power system switching, or other transient events. SPD are typically installed at the service entrance or at the equipment being protected. The effectiveness of an SPD depends on the quality of the grounding system. A well-designed grounding system provides a low impedance path for surge current, allowing the SPD to effectively divert the surge away from the protected equipment. In addition to proper grounding, it is also important to practice good housekeeping in electrical installations. Keep electrical panels clean and free of debris, and ensure that all connections are tight and secure. Loose connections can create heat and increase the risk of electrical fire. Regular inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. It is also beneficial to use proper labeling and identification of all electrical components. Clearly label all circuits, panels, and equipment to avoid confusion and to facilitate troubleshooting. Proper labeling can save time and prevent accidents. Furthermore, it is important to educate yourself and others about electrical safety. Attend training courses, read books and articles, and stay up to date on the latest electrical codes and standards. Share your knowledge with others and promote a culture of electrical safety in your workplace and community.